I'm Karl Smith with ABB, and in today's webinar, we'll be discussing ABB's arc flash protection portfolio. Let's begin with a basic overview. First, we'll introduce ABB's arc flash products and solutions to showcase ABB's advanced technology. We'll also include a product comparison of relative price and features so our customers can make a decision on which products and solutions are the best for them. We'll talk about ABB safety culture a little bit because this topic deals with personnel safety. And it'll be followed by a brief tutorial on arc flash protection. After that, we'll do a quick review of the product offering and descriptions and bring it all into context with some application examples of the REA flash system. The objective here will be twofold. One is to provide guidelines so we have criteria so our engineers understand what the principal concepts are in configuring the arc flash system, and the other is just to show actually how easy it is to configure the REA devices. We'll conclude with a presentation on the Relion relay where the arc flash option is built in, and the particular efforts here will be on the standard pre-configurations and automatic order code generated drawings that of course include the arc flash option. As you can see here, this is our protection, our complete arc flash protection offering. On the left we have the standalone REA arc protection system. And on the right, we have the Relion relays where the arc flash function is built in. Let's start with the REA, and we'll discuss the features and innovations. The REA is very, very fast. It's very economical and extremely reliable and easy to use. It operates in just a fraction of a cycle, in many cases less than in all cases less than 2.5 milliseconds and less than that. It uses the Optical arc flash technology and solid-state tripping outputs to isolate the arc very quickly. This time is negligible compared to the circuit breaker. So if you have a fast circuit breaker, there's definitely an advantage to protecting personnel and equipment. The fiber is 60 meters long. It's a loop fiber. You can constantly supervise that fiber along with the REA devices and all the connections of other REA devices made to it. So this makes this arc protection system very reliable. The extension units can expand the coverage area, can provide selectivity, so you can just isolate a small portion of the power system and optimize utilization of the power grid, the service to the customers. Also, it's very easy to use. You configure everything using the dip switches on the relay front panel. You don't have to use any kind of software to communicate with the devices. The devices communicate with each other, but you don't have to communicate with them. The REA arc flash system is very fast, operating in just a fraction of a cycle, less than 2.5 milliseconds. However, as we discussed before, you still have to consider the breaker time. So even the fastest breakers, you're approaching 100 milliseconds for a typical 3 to 5 cycle breaker operation. Here, we can use an ultra-fast earthing switch and quench the arc by creating a 3-phase short circuit to ground. The only downside, obviously, is creating that 3-phase short circuit to ground, and also you have to replace the current limiting fuses every time they blow. So, but other than that, you really can't get much quicker than this application. Now we're going to look at the speed and performance demo of the REA system to see how fast it is, to see what its capabilities are. On the left, you can we're going to generate a bolt to 3-phase fault, and we're going to clear it half a second later. And according to IEEE standards, the switchgear should contain the explosion and not catch on fire, and that meets the standards. On the right, we're going to use the REA arc flash system. We're going to trip the upstream breaker, and then we can see also that there's a significant difference in the explosion potential when you're using an REA arc flash device instead of traditional protection over current relaying, instantaneous differential. So we'll go ahead and take a look at this video. This is 5 times slow motion, and then you can see that once we have the 3-phase bolted fault, the clearing time of a half a second causes a significant explosion. There's rags in the vents to make sure that this explosion doesn't cause a fire, so that meets the criteria. As you can see, there's a significant explosion, where with the REA arc flash device, this explosion, the potential that the damage that the arc flash can cause is contained. The REA has a proven track record. There's over 3,500 REA systems worldwide in 36 different countries around the world. This is a list of end users I obtained from our pricing department. It's just a few from a very long list. So definitely we have a good reputation with our REA arc flash system. Now let's move on to Relion, and that's our very intelligent, smart microprocessor-based IED relay. And with Relion, the arc flash function is built in and is available with optional communication modules. All the logic is pre-programmed into standard default configurations. It uses lens detectors that has 3 light detection channels that use lens sensors for detecting arcing faults in the circuit breaker, bus bar, and cable compartment. You can also order high-speed output contacts as well, and to increase the speed, the typical operating time is 1 millisecond. The Relion relay operates for arc flash almost as quickly as the REA. You do have a little bit longer of a pickup time for arc flash, so it's probably about somewhere between 2.5 to 3 times the time that the REA takes to detect light and current and operate for an arc flash. Also, you're taking advantage of the advanced relay technology when you use Relion, particularly our native IEC 62850 protocol, which is now more than ever very easy to configure. The ABB relays are also highly flexible, so they're very simple to configure for high degrees of flexibility. Now that we've looked at both the REA arc flash technology and Relion relays, let's go ahead and compare the technologies, and we'll look at the difference in speed. As you can see, traditional relayings operate about an order of magnitude of a cycle more, even for the fastest differential and instantaneous elements. When you use Relion, you can decrease that operating time by about a cycle. If you use peak-to-peak measurement mode, now you can probably shave off almost another half cycle off of that. The REA operates in less than 2.5 milliseconds, so takes about half the time of even the fastest application using Relion, which is about a 5 or 6 millisecond operation. And of course, if we use the ultra-fast earthing switch, now the times are even much faster. We don't have to rely on a breaker, so essentially the arc quenching time is almost immediate. It's just the operation time of the REA and the time it takes for the earthing switch to create create a three-phase to ground fault. And you can see there it's 3.72 milliseconds, which has been verified by KEMA during testing. So it's very fast. And what's interesting there is that the trigger wire that was used to generate the fault, it didn't even melt completely before the ultra-fast earthing switch quenched the fault entirely. So certainly it's by far the fastest method to quench the arc. Here we can see just how important clearing time is. And when you look at the incident energy, which determines the severity of the arc flash fault, you can see the green and yellow colors are a little bit less, 3 and below. The red is above 4, and it's obviously much more of a hazard. The incident energy depends on the magnitude of fault current. It depends on the clearing time, which we've seen is very critical, and also the grounding of the system. You can see here that the REA relay operates very quick, and you need a very large magnitude of fault current before you're even in category 3. So very effective. The Relion is also very fast, and it's just probably in the range, just a little bit out of range of the first column. It can get into with a slow breaker, it can get into the second column, but as you can see, it is pretty fast. And there is a significant difference if you're looking at the very fastest time, affordable, versus maybe using the DFT measurement mode with Relion for a slow breaker. There certainly can be enough of a difference to want to consider that. Now let's evaluate our flash options for our products. What we'll do is we'll assume that a customer wants to buy Relion relays for main and 4 feeders, and the relays won't have any added features, just reclosing for the feeders. And we'll look at 3 scenarios. One scenario is we want to use the built-in ARC flash and Relion. The other scenario, option A, is we want to use the REA ARC flash system with the 4 REA 103 zone extension units, and the option B would be use the REA ARC flash system with the REA 105 extension units, which provides feeder selectivity. So what we're going to do is we're going to look at the trade-off between the speed that we get with these 3 scenarios versus the relative price increase. So as you can see here, we're going to establish a baseline for a customer wanting to buy Relion. It includes no added features with the exception of reclosing for feeders. And then what we'll do is we'll go ahead and order the ARC flash option on a communication card, and also high-speed output. And then the increase in price will be about 50% of what the base price would be. You do have a little bit of a trade-off with speed if you want to get it to at least close to what the REA can offer. You have to be in peak-to-peak measurement mode, which is a little bit less accurate, but for fault detection, quite adequate. Also, you're using the lens sensors, which cannot be supervised and only have 5-meter length. So there's a little bit of a trade-off, but as you can see, it's still very fast, and it certainly can meet customers' needs. Option A is with the REA ARC flash system. There is no zone selectivity, and that would be a 64% relative price increase from base. And then option B, which uses the REA and the extension units for selective tripping. Now we're just talking a couple percent higher, 66%. So now we can begin our discussion on what ARC flash is, for those that are unfamiliar or need a refresher. This is from an ABB perspective. ARC flash protection is about safety, and personnel safety. It poses a significant risk to individuals that are exposed to electrical equipment, typically 480 volts and higher. It can result in severe burns, injury, and even death. because our flash is about safety, I want to talk a little bit about ABB's safety culture. Safety is an integral part of the value pairs that define ABB's behavior and commitment to customers, employees, and stakeholders. And it really is lived every day through our actions and philosophy. Don't look the other way. It's the core value pair of 5 different value pairs is safety and integrity. And the reason I bring this up is because we all know what safety is and integrity, and I think what's unique is that ABB, we pair these values and we say safety and integrity goes together. So really it means we have to watch each other's back, and we also have to report unsafe conditions. That can be in the office where you're designing the system or commissioning in the substation. It even includes this webinar. So anytime we're talking about safety, it's, we really have to watch each other. So I think that's a good way to think about safety. So let's just find out how dangerous arc flash is. Let's go ahead and watch the video. So obviously for somebody that's never seen an arc flash, it's very dangerous. Arcing incidents do happen. According to this IEEE study, once every 18 months there's a severe arc flash, there's an arc flash injury. I know from personal experience, every company I've ever worked at has had arc flash injuries and even deaths. So this is something I think that affects all of us in this business, and also having a background in the nuclear Navy and working in many substations as a technician, I know what it's like to have been shocked. I've been shocked a couple of times. I've opened a CT, and I've never experienced firsthand an arc flash, but I've certainly heard the reports coming in from the different companies that I've worked for. So obviously it's something to take very seriously. So let's run through a very brief tutorial of arc flash. For a refresher, what is arc flash? It's the rapid release of energy due to an arcing fault between phases, neutral or ground, areas of the conductor, and it can be caused by an object too close to a conductor or insulation breakdown. How severe is it? These are some interesting statistics. It's the temperatures it can reach are 4 times the temperature of the sun. It can melt pretty much anything. The pressure, the rapid pressure expansion can lead to a violent explosion, expanding copper 67,000 times, and it's very toxic. When does it occur? It occurs when the operators work in the switchgear 65% of the time. So there's a vital statistic to, basically a call to prioritize mitigating arc flash incidences. Then here's some industry standards. Most people that work with this are familiar with what they are. The IEEE standard 1584 is for calculating the incident energy. The other standards are the procedures in place for safe operating procedures. The mitigation strategy that we'll deal with is reducing the clearing time through our high-speed tripping devices. As you can see, time is the critical factor. With 40 milliseconds, you don't have much damage or no personal injuries worth mentioning. You go a little bit faster, a little bit slower than that, and now you're starting to get into some damage and some other problems. So, like we talked about before, most conventional relays are going to put you at the 100 milliseconds or over. With the REA flash and Relion, the peak-to-peak measurement mode. Now we can start approaching that 40 milliseconds, maybe just being a little bit above it. So you can see that even just an order of magnitude of 100 milliseconds can make a big difference with arc flash, especially depending on the magnitude of fault current and the clearing times. And here you can see the relative operation speed of the different devices. Even your instantaneous and differential simply don't compare to the REA arc flash device or the Relion for that matter. The effects of faster clearing times, less incident energy like we discussed before, which may be able to decrease the arc flash boundary, the distance when the worker is exposed to 1.2 calories per centimeter squared. And it also may reduce the hazard risk category, which determines the protective clothing and personal protective equipment required. The incident energy calculation is what you see here. It depends on how fast the arc can be quenched, the time variable, and also how far you are away from it determines the amount of incident energy exposure. We'll focus on the time variable and trying to reduce that fault clearing time as much as possible. This incident energy determines the risk hazard, the hazard risk category, and the type of PPE that is required. Here's the different just take a look at the different protective clothing, and really what you can see here is that if you don't have a good arc flash protection system where there's a high risk, if you're dressed like either 0 or 1, and you should be dressed like 4, obviously that's a very dangerous situation. With the REA and Relion arc flash system, we're going to try to bring that down somewhere between 1 and 2. So, that it really you want to be as safe as possible. Here's an arc flash label. Every time a arc flash study is completed from the major software companies, it determines the arc flash boundaries, the protective clothing that's required. Here, it looks like you don't have a whole lot of incident energy, so the arc flash boundary is very close, just 8.3 inches for that 1.2 calories per centimeter squared, and the work distance, and at an 18-inch work distance, you can see you have very little incident energy, far below what can hurt you. Now that we've talked a little bit about arc flash protection, what it is and how severe it can be, now let's go ahead and introduce our products in a little bit more detail. The REA family consists of a main unit, the REA 101, and 3 extension units, the REA 103, 105, and 107. The REA 105, it has selective tripping, and it also has its own high-speed outputs to accomplish this. Let's begin by talking about the main unit, which is the REA 101. It functions as the master. It has CT inputs. You can either use those inputs for phase or ground. It has one fiber optic light sensor. It has 2 high-speed tripping outs. It has a total of 3 outputs. 2 are high-speed. It has an Optolink to transmit signals between back and forth between 2 main units, which can be either light, current, or trip. It has circuit breaker failure protection, and it has 2 RJ45 ports, so you can daisy chain extension units, 2 groups of 5. And also has alarm contact. Here's the REA 101 front panel. It has a power light. It also has 3 LEDs for the status of operation, current, light, and trip. It has LEDs if there's a relay failure. It also has LEDs to monitor the health of the connections and the sensor loops to it, to send the loop sensors, the Optolinks, connecting to the another main unit if that's used, and also the RJ45 ports for the extension units. It has a reset. You can use a binary input to reset it, or you can just push the button on the front of the panel. Here's a key which determines whether you're going to use light and current to detect, to operate the device, or just light. Here's a backlight compensation adjustment, and you can either choose automatic or manual here. This would be for the manual. And then you also have switches to configure it. Here are those switches. I'll briefly go over this now because we'll talk about it later during the examples. There's a lot of switches here, but they can be categorized, subcategorized, in just a few areas. One is they can determine the pickup of phase and ground. That's what you see here in setting group 1 and 4. You can enable backlight compensation, you can enable the sensor, and you can enable the ports for connecting other devices to it. So a lot of these switches basically just tell you how the relay is connected, how we're supervising it, what the pickup level is, what contacts that we want to use for breaker supervision and breaker failure, and also what the corresponding delay time would be for the breaker failure. This is an important note here. If you're using breaker failure, you need the key has to be in the current and light position. Here's the back panel. It shows all the different connections like we talked about. The Optolink for connecting to another main unit. You have two of them, one for transmit, and you can program for transmit or receive from the other unit. Here's the loop fiber sensor port, the RJ45s for daisy chaining, the internal relay failure, the tripping outputs. Remember, it contains 2 high speed and 1 normal rated trip output, trip 3. Here you can connect your control power, and that pretty much includes all the levels that we're used to in the United States, 24, 48, 120. It also has AC control power. Here you can use the binary input to reset, and here's all of your CT inputs. This right here is the connection diagram showing how those switches are situated in basically what's a logic block diagram. And when I was going through this and trying to understand how the different applications work, this is a very useful diagram. It allows you to trace all the different current and light and trip signals from device to device to determine, to predict how the system's going to behave. So it can be a good troubleshooting tool, and also can be a good tool just to understand how the devices work. Over to the right, you can say you can connect your CTs. You can use either a zero sequence CT or a residual for the ground input. You use the other 2 CTs for phase inputs, or you can just use 3-phase inputs. And there you can use the 1 or 5 amp nominal rating. Now let's move on to the REA 103. This has 2 fiber optic loop sensors. It doesn't do any tripping. What it does is it detects light, sends it back to the main unit, which does the tripping. It has a couple of alarm contacts. These are not tripping contacts. They're just used for alarm. And you got the RJ45 ports for connecting additional extension units. Here's a look at the front panel. Let's start with the switch. You know, with the extension units, you can daisy chain several together to protect multiple feeders. So the last one in a chain has to be terminated. That's what the setting is. Here's backlight compensation. Here's your sensor enabling if you're going to use both sensors. And here you have sensor supervision deactivation, which the default is off, meaning that if your deactivation is off, you are supervising the loop. So if you're using loop sensors, then obviously you have got the capability to self-supervise the sensor. If it's a lens sensor, obviously that switch has to be on, which means it's deactivated because you can't supervise a lens sensor, but you can supervise a loop. Now let's get to talk about the RA105. That has one loop sensor. It has two high-speed tripping outputs, alarm contact, and 3RJ45 ports. You can connect this either to the main or to additional extension units. The reason here you want to connect it to the main is because the main provides current information to the RA105, and if light is also detected, then it trips its own high-speed outputs, making it selective. Here's a look at the front panel. Here you've got two inputs, so depending on, if it's the last one in the daisy chain that you terminate, depending on which input it is on determines which switch is used for termination. Here's your backlight compensation. It can be either automatic or manual, enabling the sensor. I want to focus on this a little bit. Light to port input 1, which really means you're using input 1 to send light back to the main unit. Here's breaker failure. You can delay that light signal for breaker failure situations, and if you do, then you'd have to turn the light to the off, so you can, in breaker failure situations, delay the light signal back to the main unit, which is going to do the tripping in the event of the breaker failure. Here's the breaker failure delay, and then your loop sensor, your activation, your supervision of that loop sensor. Here's the connection diagram, similar to what we looked at before. Now we'll look at the RA107. That contains 8 lens sensors, and it operates similar to the RA103. It just detects light, passes that signal back to the RA101, which does the tripping. Here's the front panel. You can enable all your sensors, backlight compensation, and you have to terminate the last one in the string. So pretty self-explanatory what's here in terms of the hardware. Here's the logic diagram. And so you can use all of these block logic diagrams with switch settings to predict how your system is going to operate, good for troubleshooting. Here's a look at the optical fiber sensors. Not too much my area, but I have studied this somewhat before. I'll just highlight that you can use up to a 60-meter length for the loop sensors with one splice. Here's the optical lens sensors for the REA107. Then you have your Optolink communication up to 40 meters in length. Something to talk about here is if you're connecting two mains and two different switch gears, they have to be verified at the same potential, otherwise you can't use the Optolink. But you can connect the mains via a 105 unit via RJ45. Here you have your RJ45 cables up to 40 meters and the splice adapter. Now to bring it all into context, we'll go ahead and look at some examples. And our objectives are one to look at the things that we need to consider that are best suited for the customer application. And we also are going to demonstrate how easy it is to set up a system and configure it. The objectives here, what we want to look at is the main objectives are to minimize the incident energy, of course, to safe levels. That's done by fast clearing times, fast tripping. We also want to optimize utilization of the power system, and that can be done with selective tripping. The other thing that's also important to look at is we have to evaluate the impact of added incident energy for breaker failure contingencies if delayed tripping is used. So if you want selective tripping and you have a breaker failure, then keep in mind that the breaker failure delay will add incident energy, and if you didn't use the breaker failure, and have fast parallel tripping, even if you had a breaker failure contingency, you would still be operating at speeds negligible to the breaker. So that just has to be considered and has to be evaluated when looking at breaker failure. Now we're going to bring into context what we just discussed, and these examples will help us understand what the criteria is so we can apply these objectives. Here we have a power system configuration of one transformer connected to a single bus, and we're using a main unit for this arc flash protection system. You have a two-phase and CTs and a ground CT residual. The residual CT is connected to the ground input. You're using the high-speed output to trip breaker Q2, and then for breaker failure, which is set, will trip Q1. The loop sensor is protecting the bus, feeder, breaker, and terminations. And so if we have an arcing fault, we'll detect light, we'll detect current, and the high-speed output 1 will operate in less than 2.5 milliseconds, a fraction of a cycle, and issue a trip to Q2. If you have a successful trip, then there should be minimal damage. If personnel are exposed, then that they should be safe, and then you can go ahead and close back in Q2 and restore service. If you have a breaker failure on Q2, then a pre-programmed delay after high-speed output contact 2 will operate and trip breaker Q1 or high side circuits, which are adding a little bit of its energy due to the delay. Let's go ahead and see how we set the switches for this application. So this is the main unit, all the switch settings shown here for the main unit. Setting group 1, the first 4 switches determine the phase pickup, so it's 1 amp per unit of the nominal. In this case, we're not using backlight, automatic backlight compensation. We're enabling our sensor, and there's nothing else connected to it, so these port settings are off. Also, because there's no other main connected to it, we're not using the Optolink, and these switch settings are not applicable. So they're left at default, which is the switches are in the opposition. Setting group 3, the first 3 switches are used for breaker failure. The first 2 here allow the user to select which contacts he wants to use for breaker failure, which is high-speed output 2. Here's the corresponding breaker failure delay, and we will supervise the loop, which is deactivation off or loop circuit supervision. Because we're using a ground input, we set the ground pickup with the first 4 switches, 0.3 amps per unit of the nominal, and then we enable the ground current, the I0, that switch is on. Now let's take a look at a little bit more complexity in example 2. What we're going to add now is REA extension units. So you can see here now we're going to connect just three-phase input to the device. The contacts are used as before for Q1 and Q2. On port A, we're going to connect the REA 105 extension units. On port B, we're going to connect the REA 103 extension units. The REA 103 extension units have loop sensors that just detect light. That information is passed to the main unit, which does the tripping, so you don't have any selectivity. The REA 105s, they receive, if you have an arc flash in their zone of protection, then if you exceed the pickup value, if the current exceeds the pickup value of the fault detector, then this pickup signal is passed on down to the REA 105 units, and if they detect light, they will high-speed trip on their own output contacts. The main is just as we discussed before. So now if we look at a contingency here, let's say that we have an arcing fault on one of the feeders. Then we're going to trip Q4. If it trips successfully, then we have selective tripping and we've isolated it from the rest of the system. If we have a breaker failure, then what we'll do is delay the light signal from the RE105 unit to the main unit, and then after a pre-programmed delay, we will trip breaker Q2, and of course this will add just a little bit more incident energy to the system. And if Q2 fails, then from the discussion before, after a delay, we'll trip Q1. So let's take a look and see what the switch settings look like for this. Really for the main unit, the only difference is the fact that you're connecting the port settings to the extension units, so they will be on. You still don't have anything, you're not connecting to another main unit, so this is inapplicable like we discussed before. For breaker failure, we are going to use high speed, just like before, the high speed output contact 2, so that's the same. In this case, we're not using the ground input, so these switches won't matter because we've turned switch 5 off, which disables the ground input. S1 and S2, as you can see here, are the REA extension 103 extension units, and there's 2 of them in the chain. The last one is S2, so we need to terminate that. That's what that's for. The rest of it's like we discussed before: backlight compensation, enabling the sensors, supervising the loops. Now let's take a look at S3 and S4, which is the REA105 extension units. You can see that the S3 unit is the last in the string on input 1. That gets terminated. And then for breaker failure, what we want to do is we have to have this light to the main, light via input 1 to the main off. And then we can use breaker failure and also keep, so that's something to keep in mind. And then we can set this switch to on, which delays the light to the main unit after a pre-programmed delay. So if you have a breaker failure condition, then the delayed light signal will cause the main to trip Q2 to clear the fault. You don't have your selectivity. You also add a little bit of incident energy to the system. Now let's take a look at example 3, and mainly what I want to show here is that an application where you're using the Optolink. This is for a main tie main scheme, and we will not have breaker failure in use. And what we'll do is say that somebody's working in the switch gear that if any of these breakers fail, Q6, Q7, Q2, then we're going to have fast parallel tripping to keep the incident energy as low as possible. And we'll see what our options are in terms of opening the upstream breaker if we don't have breaker failure protection in use. So let's take a look at what the switch settings would be like. For the main, you're using port A but not port B. Everything is like we discussed before. Here you are using the Optolink, and what you're doing is you're on Optolink 1, you're receiving the pickup of value. That's when the current measurement exceeds the pickup, and then the fault detector is active, so you're receiving a pickup signal from the other main unit, and you're also transmitting this pickup signal to the other main unit on Optolink 2. We're not using breaker failure. We're not using the ground pickup in this case, 3-phase CT inputs. So here for the second main, we're not connecting anything to it, so those port settings will be off. We do have the Optolink connected. In this case, it'll be just the opposite from what the main one is. We will be, in this case, we'll be transmitting current on Optolink 1, and we'll be receiving on Optolink 2, so it's set as an input, off is the output. Output is transmit, and input is receive. So transmitting on Optolink 1 and receiving on Optolink 2. Now using breaker failure, no ground input connected. Now we'll look at the switch settings for the REA 105 extension units. Here I turn breaker failure off, and the light to the port input 1, the light to the main, has been turned on. The reason I did this is just, it's not a typical application. You want the 105 when your application calls for selectivity, but you do have that capability. So as long as you're not using breaker failure, then you can have the switch on. If you are using it, it has to be off. So I just want to let you know you can have the switch on. You can send light to the main unit, and if the main unit sees current, then you're going to trip very fast the low side breaker, and so you don't have any increase in incident energy. So really this would be like for a maximum protection situation. Now let's say that you don't want to keep this switch off, you don't want breaker failure, and if this switch is off because it's not a typical application like I just mentioned, then what's going to happen is you can detect arcing faults, and if you have a breaker failure, then something's got to clear that condition. So if you're not sending light back to the main unit to trip, then you're going to have to rely on the speed of your main overcurrent protection for that. So you are going to have a little bit of incident energy in that situation. So really it's just a matter of evaluating what you're comfortable with and seeing how fast your overcurrent protection is operating, how much incident energy is added due to the breaker delay, and then obviously the more conservative approach would be the fast parallel tripping. Now let's discuss the Relion family of IEDs, and this has the built-in arc flash. In order to get the arc flash option, the detectors are on the communication module, and then so you have to have the right order code in order to get the Relion with the arc flash option. Also, it's recommended to use high-speed output since that's programmed into our default configurations, and so you have several binary I/O options that include high-speed outputs. Here are the standard pre-configurations that we talked about, your arc flash. You have protection blocks, function blocks for the arc flash units, and they can be the signals, the output signals, the trip signals can be connected to the master trip, and also other high-speed output contacts. So you don't have to do any configuring logic. That's already been done for you. We also have drawings to order code. It's a project I've been working on. You can enter any order code you want, get a full complement of drawings, functional, detailed one lines like you see here. AC and DC schematics, pre-wired connection diagrams. Here we have an order code where we selected arc flash. That's what you see here, digits 9 and 10, and then the arc flash shows up. You have your level detection, your current detection for arc flash. Similar to the way the REA works, current and light. And then on the left side, you can see how the once these arc flash signals are active, how they work with the the logic to perform the trips. Here's an FT1 arrangement. So, we prepackage the solution with our FT1s. And when you select the arc flash option, your FT1s for your arc flash trips are pre-wired to the relays. AC schematic. DC schematic, here's your high-speed outputs, here's your switches. And then you have your pre-wired solution here for the arc flash trips to the switches. Here's an example of using Relion for arc flash. This would be similar to the using the 105 extension units for REA, because they have their own high-speed tripping outputs. And here is a main REA unit. You could use a main, like in the comparison examples, to protect the main breaker and arc flash coverage for the bus. Keep in mind too that they're very fast, and there's not really too much of a trade-off, but in some cases it can be significant, and either way it's a good choice, and we want to keep the options open to our customers. We have a 12-year warranty on our relays, and I appreciate you all for attending this webinar, and hopefully I've provided some insight and offered some guidance on how we can select the products and choose which solutions are best for your application. So with that, once again, thank you.